Okay, as you read already, we are going to talk about the superconducting cables for fusion and the effective field that is present in there. First of all, to introduce you in the topic, I'm going to talk about the arguments to study the new cable layouts. As we already know, the goal of fusion research is to produce energy, and because already we fuse atoms, but we want to get more energy that we invest. This means improve the performance, and for improve the performance is also very good and make a more effective reaction and invest less energy and try to reduce the investment of energy than the energy that we gain. And one of the most consumption of energy goes to the fusion magnets. This is the way because it's important to try to improve it and get it in better ways to produce more effective reactions and has some profit of energy. And this is the motivation for study the new cross-section designs. First section is about the fusion magnets. I'm going to introduce you in fusion magnets and why superconductors are used. First of all, talk briefly about the two kind of reactors that already are more popular with magnets. These are the tokamak and the stellarator. The tokamak is already more developed and is first candidate to next generation station, power generation station. However, it needs correction coils and has also some drawbacks. And about the stellarator, also promise very much because it's a device without plasma currents that produce a lot of instabilities in plasma. But however, it has a complex coil systems that make it tricky to realize it, and already has lower performance than the tokamak, or let's say the next future tokamaks. So the topic for today is superconducting magnets in tokamaks, not in stellarators. That will be other totally different study. Then, what we use as magnets in fusion? Superconductors, because they produce large magnetic fields. That is what we want for put some pressure in the plasma and confine it. These magnetic fields are produced by very high currents, and this is an example of how will be the magnetic fields in ether and the currents in the different magnets for each part. And this study is focused on the toroidal field coils that are the one that use more current, so need to be very effective superconductors and be allowed to carry out of current. And as we said, it is about the low temperature superconductors. Well, not only low temperature, but also let's talk about superconductivity briefly. Superconductors that are used for fusion are type 2 superconductors, and the reason is because they can support more magnetic fields than the type 1. The superconductors are diamagnetic materials, so that means that the magnetic external fields don't cross for the materials, but in the case of type 2, it allows a partial penetration of magnetic field, and this reaches a superconductivity critical external magnetic field higher than the type 1. This is produced by a physical phenomena that is produced for small vortex in small impurities put in the material that maintains the critical current density and allows penetration of the magnetic fields. This is a scheme of what are the critical values for superconductors. We see the example of the two superconducting material used in ITER, the niobium stanium and the niobium titanium. And we see that if we go very high in one of the variables, the other then goes really low. So the materials used already are these two that I introduced you. Both are low temperature superconductors, type 2 superconductors. That means that they use helium as coolant. The difference is that the niobium tin is a brittle material, so it is very difficult to manufacture it and to process it. And in the other hand, you have the niobium titanium that is very ductile material and very easy to manufacture. But we need the niobium tin because it has larger magnetic fields, while the niobium titanium has a limit in 9 Teslas. That means that the first one gives more performance, but in the future, the niobium titanium can be substituted by Ribco tapes. Promises better performances, but don't really like the niobium tin. As I told, it's brittle material and the manufacturer gets expensive, so would be interesting to use the other one, but the first one, the niobium tin, is necessary because of the larger magnetic fields. And is used in the toroidal field and central solenoid coils because, as I saw before, in ITER they are very high, around 12 Teslas, but the lower necessary magnetic fields can be produced with niobium titanium, or we hope in the future with high temperature superconductors. Okay, now we are focused in the niobium tin, that is the superconductor that is analyzed in this study. And we are going to see how is a cable in conduit conductor in the toroidal field coil. This is an example for ITER. Is round conductor. It has a steel jacket to support the high Lorentz forces, and its cable of ITER is tested with cycling loading to really see if it will work or not. Because if you assemble these cables and then some imperfection produce the destroy of the brittle material, then you have to change the coil and it's huge costly. So the point is that they are tested, they are prepared for the Lorentz force to the other conductors, and they has the circle that is inside is for the cooling. There is inside of the cable flowing supercritical helium that gets the low temperature necessary for produce the superconducting state. This is easier to manufacture than the rectangular ones, and as we can see, it's divided by 6 petals and twist the petals to avoid the alternate current losses. Is mix the superconducting materials with copper strands. We will go inside in the next slides. It needs a heat treatment to become superconducting, and this is the distribution in a toroidal field coil that is divided by pancakes. Okay, then we have presented the circular, and these are the prototypes for square and rectangular low temperature superconductors on niobium tin for TF coils and for ITER. Well, in this case, not for ITER, but for demo and future reactors. These are the proposed. One is from INEA, the Italy Research Institute. Other one is from Switzerland. The one up right is from the place that this study was done. And the square one is from SIA from France. they have similar structure than the round one, the same material, but they innovate on the layer distribution because they have to. I mean, it's also twisted but the as we can see, the cooling channels are different distributed. In the up left we see two inside cooling channels. In the up right we see external cooling channels, but of course the cooling is always through between the strands of the conductor. And these kind of conductors can be most robust for the wind impact because they will have less space between them, and it will be better for Lorentz forces supporting. There is two possible winding techniques like winding and react and wind, but it depends. They are used different on these three prototypes, and it's not very clear which one is better. Ones have more advantages and other ones. Well, and we are already presented pointedly what we are going to do. And now we are going to talk about the equations. Yeah. This is more technical part about the critical current density and the current sharing temperature. Okay, the first thing that I have to calculate is the strain function that is a scaling law already, and it's produced by the strain applied to the conductors plus the maximum strain. You see also non-axial residual strain, strain shift component, some constants in the scaling law. And this is the equation that I have used for calculate the strain. And this is the function of the critical current density with the strain. Usually the strain in these cycling loadings goes from minus 10 to plus 5. It's in percent, yeah. And this is the result. If there will be no strain, of course, the critical current density will be higher. But because of this strain, this gets low. And this is the scaling law for the critical current density that depends on the strain function, constant C, magnetic field B, and the small t and b are minimize temperature and magnetic field. Well, the current sharing phenomenon. This is about the current sharing temperature. Superconductors only conduct at very low temperature, around 4.2 K. And the thing is that if some perturbation occur in these materials of superconducting cables, it can share its current because each strand is surrounded by copper. So as we see in A picture, the current goes to copper when there is one perturbation, then it's flowing through the copper, and to get again after the perturbation, the copper is cooled down with this liquid helium that remains very low resistance and permits the flowing of the current. Yeah, this is what I said. And the liquid helium is flowing through these gaps that we can see in the image. The copper is in direct contact with the cooler through the gaps, and if temperature increase is not stopped by the copper's by the sharing of current, it could become inaquench and destroy permanently the superconductor. So this is very important and very critical. We have here a set of the current sharing temperature. This is for the 10 microvolts per meter, and this is set experimentally. It's not a specific one, it's one safe limit. And as we see, if we are under the temperature of current sharing, we have no problem, we have no electric field, the superconducting behaves good. And if we overcome that temperature, the electric field rises very, very, very fast. And we will be in between the current sharing and the critical temperature at which the superconductors get destroyed. So in this gap, in this space between the two limits, the current can come again to the superconductor and nothing happen. But if it goes higher, then a quench is produced, and this is destroying the magnets. Well, and now this is the MATLAB assessment that we use. Already with the critical current density, we calculate it for one conductor, but the point is that because there is a magnetic field in each conductor, it's not the same critical current density in each point of the section of the conductor. So we assess, and this is only an example comparison, a round conductor and a rectangular one with the same area, and we use the same current, same temperature, same strain, and the background magnetic field is only on the y-axis. So for your screen will be from the right to the left, and the critical electric field is already set. The critical current density is set by the scaling law, and then the study of MATLAB will be for each point of the section. So the critical current density will change if we make the mean of every of these points of the section, and we will see why. Important to take in account that in the graphics that we are going to see, the current is going in the direction of the green cable that we are seeing, and the magnetic field is in the direction that is already plotted. So remember that the external magnetic field that comes from the other conductors, in this case, is only an example for comparison, comes from right to the left. So the lines that are more close to you already will be in counter, and the other ones will be at the same direction. Then we see here the y-axis in the round, and we see that the magnetic field average increase, so because of the internal cable, and we see also the maximum and minimum values, and we say also the example of the rectangular conductor, and also we see the y-axis, and the direction is from negative to positive. So then this is not conclusive, but we see that there is a bit more on the round. Then with this equation, we calculate the electric field depending on the current density and the n factor that we defined previously as 10. Then this is the difference of electric fields. You can see the data. This is also higher in the round one example. And then we see the current shared temperatures. We do already, I did one running for each of these temperatures with all the points of the cross section, and after that making a mean, you obtain these two lines, and in the point where the electric field is critical, we get the sharing temperature, and we see already that the sharing temperature is higher in the rectangular conductor, which is what we want. We have higher current sharing temperature, we avoid this phenomena during more time in case of perturbance or if something goes wrong. Then with this, we are going to calculate the effective magnetic field. We use the current sharing temperature as the point of most critical state of the function of superconductors. And now we compare the scaling law of the critical current density for the whole magnet with the mean that we obtain in the MATLAB assessment using this temperature in both of them, the current sharing temperature. And we see that for 10 Tesla, it is higher current density, higher critical current density on the MATLAB assessment. So we get it at the same position, and at the same critical current density, we found two effective magnetic fields. And this is the effective magnetic field exposed, the magnetic field that the cable is supporting or affected by during the work. So already we see that the rectangular ones has less effect or feels less effect on the external magnetic field. So the effective magnetic field is lower, which is better because with lower external magnetic fields, we have better or more limits for the critical current density. Well, the point is that you have larger limits for temperature and for current density. This example is only for comparison, and it's important to say this because in the assessment of MATLAB, we already do like the whole area is superconducting area, while in fact it's part superconducting, part copper, and part gaps. So this is already only for comparison between the two shapes, but it's enough for that. And these are the results depending on the aspect ratio and the conclusions. First, for the for the current sharing temperature, we see that the round, we already know, has very low one, and the first example of a square has better performance, but not much different. However, if we go to larger ratios, we found larger current sharing temperatures, which is better. And if we see even more large ratios, we see that from 20 or 1/20 ratios, the increase gets low and is not that pronounced. Well, if we get very small, compare how is better if the conductor is in the more is in the same line of the external magnetic field or not. We see that the Y already, when the Y ratio is larger, and this line is in the same line of in the same direction of the magnetic field, we see a small, very tiny, better performance, but it's also important to see it. And we see the opposite with the magnetic effective field that is going down, so the conductor feel less magnetic field in the whole conductor when the ratio is bigger. We see the same example with data now, comparing the square when the ratio is 1 and the round, and when it goes to rectangular, very wide rectangular, you see that it's also mitigated the effect. And there is also, for this small scale of 1,2 to 2,1, this difference when it is aligned with the external magnetic field. That is tiny, but important to see. So the final conclusions. For the current sharing temperature and the magnetic effective field and the same conductor area, we have that the rectangular is better than circular. Then the rectangular is better than square sections. Then larger aspect ratios are better and more square aspect ratios. And just to finish it, the magnetic field parallel to the larger side is slightly better than B across it. Of course, other factors influence the conductor's design, as the economical cost, the alternate current losses, or the material's performance, as many others. But this is one important thing that is important to have well studied, and we already see how it is developed. So thank you for your attention, and this is all for me.
Perdón. Sorry, I lost the audio button for a sec. Thank you so much for this talk. Very interesting and beautiful presentation. And well, the stage is up for questions. So feel free to raise your hand in the participant box. And if there are no questions for now, maybe I will start. If you go back like way at the beginning, you were talking about niobium tin and what's the other one? Niobium titanium, right?
Yeah.
Those are like the two candidates. So you said the niobium tin has in general like a better performance, but it's brittle. What's the ductile to brittle transition temperature? Do you have this?
Well, what do you mean already?
Well, so I think all materials have this temperature at which they go from ductile to brittle. I assume that if you say it's brittle and it's a limiting factor, it's going to be brittle over the range of operation, but like how high in temperature would you have to go to? Because maybe you could manufacture it at a temperature at which it's, you know, not brittle, and then it doesn't matter if it's brittle when it's installed.
Well, the point is that the niobium tin is very complex. Well, not complex, but a special crystalline structure. And it's because also this crystalline structure that it can get more current inside and then produce larger magnetic fields. So this is because it's worth to continue the research on this material.
Mm-hmm. Okay. And do you know the limit, the magnetic field limit on the niobium tin side? You mentioned it on the niobium titanium, but not for the niobium.
Well, I don't know exactly, but as reference, you can see in the
right, there's this plot.
Reference that the maximum for the central solenoid is 13 Teslas. So it's quite high.
Right, but this one would be, yeah, that one would be also constrained by the machine and the physics of the machine itself, right?
Yes.
It's better to look at it in the 3D plot that you give in the next slide, right?
3D plot? Which one?
Those sort of pyramids.
This? No. Which one?
I guess no. Further down, but I guess I can look at it later. I now that you went past it, I know that it's there. So this one, yeah.
Okay, this.
Yeah. So I guess there it is, right? Magnetic.
Yeah. Where you're talking about the critical values.
Yeah.
Well, but you see that anyway, you cannot go very far in critical values because you lose the two others.
Mm-hmm.
So that is the point. I mean, now here you can see that the niobium tin can reach the 25 Teslas. But at 25 Teslas, the critical density will be maybe, I don't know, 200 amperes per millimeter square, or maybe less. No.
And it doesn't make sense, exactly.
Yeah.
So do you know what the practical limit is? Like if you want to make a magnet for like a fusion device, you want to use this niobium tin because it's better than the niobium titanium, and you're able to manufacture it until when does it make sense? Because I mean, I could maybe take a guess for the temperature, but I wouldn't be able.
Yeah, but already the manufacturing is very complex because as type 2 superconductor, it needs to have some impurities that pin in the vortices where the magnetic field is going to cross. And this is the reason also because it's very discussed between the react and blend and react, because sometimes it's good one, sometimes it's good the other, but there is already an active research on this, and they are already getting some surprises for good and bad. So the point is that if they improve the manufacturing, these limits can grow up. But this is already the most extreme limits that already we know. And if this grow up, needs the niobium team, because already there is no other material like it, like the niobium team, in terms of manufacturing plus effective production of magnetic fields plus resistance to the high currents. I mean, of course, I already saw what happened if a quench happened, the superconductor get destroyed. But this is very well known and this is very well studied. And yeah, I already just to take in the presentation, I take some small details, you know, but there is long research on this, and already the manufacturing is known, but they are still looking for improve.
Okay. Would you say that the current ether magnets is the best we can do with niobium tin right now? If we had to build, if you had to build a niobium tin magnet for a fusion reactor, like you build it today, the fusion reactor is there tomorrow. I know it's completely unreal, but is that the best we can do?
If you need that strong magnetic fields, yes.
Okay. And you mentioned the wind and react. So what is react exactly? Is it like a heat treatment?
It's the treatment of heat that the superconductors receive to be homogeneous and to distribute the impurities for the pinning these vortices and allow the second type. I mean, yeah, the point is that the critical magnetic field is improved in type 2 as much magnetic field can go across the superconductor, and to do the material properly well for this effect, you have to put it to very high temperatures to melt it, cool down, then melt it again, and do it that process to get it very homogeneous and consistent material. But this also make it difficult to manufacture and make it very brittle.
Okay. Well, I don't see a hand yet. Oh, question in the chat. So I guess I'll read it out loud. I have a question. A question comes from Alex Vasquez. I have a question regarding the manufacturing of the superconducting magnets. Do the wiring techniques differ much from the tokamak to the stellarator?
Yeah, I'm reading. Yeah, the point is that already I know that it's more difficult for complex magnetic systems, but I don't know what are exactly the constraints, because for this scope I only look on tokamaks. I don't touch nothing of the crazy coils of stellarators. But of course, for welding that and blending that coils, it will need a special treatment. That's for sure. So it's more complicated make that shapes than make a D shape of a tokamak. That is for sure.
Okay. So, well, in the meantime, I'll ask another one maybe. Can you go back to that first scaling law you showed about strains?
About the strain. Yeah, the strain function, yeah.
I was a bit curious about the terms. Like, what do you call a strain invariant? Like, it doesn't
Well,
change if the strain increases, or and what is it
yeah,
related
the point is that the strain is due kind of forces that are produced in the material when the current is flowing, and this is like the percentage that the material suffer the strain. But this is already a scaling law that I took from, I think was one paper of demo. I'm not sure, but I think. And it combines like the different kind of maximum strains and applies also some constant that are taken from experiments. So it's quite complex, but the point is that that is small percentage from 5 to 10% to minus 10 already.
Okay.
But yeah, if you want, I can send you the thesis, because there is not only the reference but a brief introduction to each term and where it comes and why it is used. So in the main thesis you can see.
Yeah, if you can do that, that'd be great. And I guess that would answer also my next question about the minimized temperature and beta. Is that like a normalized? Are those normalized values?
Yeah, of course it's normalized. That is also another scaling law. But this scaling law was a mixture of 3 or 4 models. So, I mean, the strain function is one model, and here we see the dependence of the strain of the critical current density that is very high. I mean, for very small variation of the strain, you lose practically half or almost half of the limit of the density current. And the point is that this one part, the minimized or normalized temperature and magnetic fields depends on the temperature of the superconductor, on the magnetic field, the external magnetic field. P and Q are constants, that is for sure. And for example, yeah, this is the point, because this equation varies when you reach the certain temperature, and this is what produced that high rise of the electric field. So it's because of this limit. When you increase the temperature, this limit gets very, very low. I think that the equation of the electric field is somewhere in the MATLAB's simulation. Yeah, it's here, you see?
Okay.
So when the limit of the critical density, current density, goes very low, the electric field just blow up, as you can see here. So that normalized temperature is for calculate this trigger.
Okay. Okay, thanks. Okay, so maybe I'll ask my last question since I don't see a hand in the participant box.
Yeah, Francis already has one question.
Oh, does he?
Yeah. The P and the Q, yeah, the question is, what does P and Q stands for in the equation of current density equation? Well, I know there are constant, but I don't really remember where they come. Yeah, but this is something that I can send you the thesis also, and there is explained and also the references.
Okay, I guess he sent you the question directly because I couldn't see it.
Yeah.
So do you have any other questions in your chat box?
No.
Okay, so maybe I'll ask a last one about the concluding slide.
Yes.
So when moving from this circular cross-section to a rectangular cross-section, considering the square one, then changing the aspect ratio and the direction of the field, I had the impression, but then of course it's might be a matter of scale, in when I saw the view graphs that the changes were not all that big. So do you think the changes justify from an economical and a technical standpoint the use of a different cross section? Because you said they were harder to manufacture.
Already that is true, are harder to manufacture, but the point is that this is one assessment about the current sharing temperature and effective magnetic field. But this is, I don't know which percent, but maybe it's 10% to have a final decision. Because it's not only the manufacturer, it's not only the economical, it's also the AC losses, it's also the robustness that win the coil, the materials performance, depending also on the high temperature. But for these two aspects, it's worth to make it rectangular. At least we know that it's not worst. And only for this, I mean, of course, to take a final decision, you have to consider all. But already demo and I think new designs are all on rectangular shapes.
Oh, so it's not that difficult. Or maybe there are other things that's strong.
Yeah, I don't know the magnitude already of the difference.
Because I feel like the at least for example for the V effective, the change that you showed us, it's something like 0.5%, which I don't know if it's
but this is
deal,
you cannot take that in account because already that is this is very small difference here in the current temperature, and very tiny difference also here in the magnetic effective field.
Yeah,
but
that's the number
this is not conclusive because this is one ratio that I used, very simple, only for comparison and to put some plots, of course. But then the real aspects that you have to consider is here in this graphic, because here you see if you put order of 120 or 20 ratios, then you get very difference with the circular one. Well, this is still 10, but let's say that 0.1 is changing. You see here better. 0.1 is changing from circular to these ratios of 120, and the effective field something similar.
Well,
you see here that ratio of 20 goes from 0.5 to in circular is 0.19. So from 0.19 0.05. It's not too much, but the point is that 10 is the minimum. So really reduce the effective magnetic field.
Okay. Yeah. Yeah, but okay.
Well, of course, for example, this consideration is not really
okay. It is a 10%.
important or worth, but